Okay, welcome to the second week of this course. In the first week, we learnt about new ideas like constraints, generalized coordinates, configuration spaces, and so on. And then finally, we use the D'Alembert's principle to derive Lagrange's equations. So, that basically summarizes the program of classical mechanics. What I will do is first pose the dynamical problem here. See, even if you are considering a single particle, what is it that you want to do? If we know all the forces on the particle, then if we know its initial position and its initial velocity, then we want to predict the path that it is going to take. Okay. And then of all the paths that it can possibly choose, which path will it take? It will take one of those paths which satisfies the Newton's laws, okay, which is given as a form of a differential equation, which is m r double dot is equal to force, which may be function of r dot and t and so on. Even if you take more complicated system with all the constraints thrown in, with potentials given and so on, even then the problem really reduces to, now you are going to describe the system in terms of a path in a configuration space. Okay. So, you put everything together, constraints, then you find out the accessible configuration space, and then your system as a whole is just one point in that configuration space. And if we know the initial conditions, that is, if we know q and q dot at some instant of time, then we want to predict the path of the system in configuration space at some later time t. And which path would it take? Again, you have these Lagrange's equations, which are second order differential equations, and you would say that a path taken by the system is the one which satisfies the Lagrange's equation. Now, you see, for us, for people who believe in nature, it's slightly uncomfortable feeling that it's so technical definition of which path the system is going to take. It's very mathematical definition. It doesn't seem to sort of give a nice idea. Remember, it's a field, nice idea about what nature is going to do, and that's where the Hamilton's principle come in. And the Hamilton principle, this is very elegant principle, that it says that the nature chooses that path which has the least action. And so, of course, we will have to make a technical definition of action, but there is a elegance in this statement. It sounds nice, but of course, underneath there is mathematical definition, of course, but it's such a simple statement. And then in the course of this week, we will show that the Hamilton's principle is also equivalent to Lagrange's equations or a Newtonian formulation that. So, this is our program for this week. Now, I will start the introduction with a classic puzzle. Okay. Look at this diagram here. In this diagram, it's like a big field which is 100 meters by 100 meters, and on the left side of that field is the concrete, and on the right hand side, on the right half, there is a sand, and there are these diagonal points which are marked as A and B, and the aim is to go from A to B in shortest possible time. Okay. What is the catch? Catch is this: concrete is a nice hard surface, you can run on it with a speed which is 4 meters per second, but on sand you can't run as fast as that. So, for example, I have taken that to be 2 meters per second. Okay. Now, which path is the question? The path that would take the least amount of time. Now, as far as the concrete is concerned, we can immediately figure out how to do this, because in the concrete region the time taken would be length of the path divided by the velocity, which is fixed. So, basically we should be running in a straight lines on concrete and in straight lines on the sand. Okay. So, if you do not know the answer, you probably want to pause the video here, think about the answer and then start again. So, here what we must do is run in the concrete in straight line, run in the sand in straight line. How about a path like this? So, a path must be somewhat like this, but this of course is not a pretty good example. How about the diagonal path? See, the diagonal path is the shortest path, but since we can run faster in concrete, it is common sense that you probably should run longer distance or as much distance in concrete as possible to get the shorter time. So, probably we might think of a path like this. In this path, you would run all the way from A to the upper corner of the interface and then run parallel to point B. Now, here is the comparison of these paths. So, the green path, which is diagonal, which is shortest, about 141 meters, it takes about 53 seconds. But wait, that red path is about 162 meters, but it takes tiny bit less amount of time. So, you are running much longer distance, but still you would end up taking less time. Okay. So, question is, how do I find, is there a path somewhere in between the green path and red path which probably is the shortest time path? So, how do we find this? One of the ways you can do is simply search for a path. Now, we have already figured out what is the nature of the path. So, what I will do is, there is a point of crossing from concrete to sand, and let us say from the bottom of the picture to the crossing point, that distance actually defines the path completely, okay, where you are going to cross, because once you fix the crossing point, A to that crossing point is a straight line and crossing point to B is another straight line. Okay. So, here what I have done in this one is, you can actually change the path as a function of crossing point here. So, on the right hand side of the graph, you have this crossing point and we have just crossed the midway mark, and there you go. The time taken, which is plotted on this graph on the right hand side, immediately shows that between that diagonal path and the extreme path on the where you run all the way to the top of the figure, somewhere there at about 76.91 meters, you have a best time path, and which takes about 50.5 seconds, and the distance run is of course larger than the diagonal path, but this is the one we wanted to find. Okay. Now, there is another way, use calculus. See, since we already have figured out the nature of the path, calculating the time for this path is very easy. So, the path can easily be given by an integral of ds over v, where ds is a small length element along the path, and then because the velocities on concrete side is fixed, velocity on the sand side is fixed, the formula can be immediately integrated to something like this. So, here is the time. Now, all we want to do is find a path or a crossing point where this particular time would be minimal. So, all that we do is take a derivative of this with respect to L, that is the distance of the crossing point, and set it equal to 0, that immediately gives you a value of L as 76.91 meters. Okay. So, this is the but there is something more to this problem which I wanted to show you, and that is, if I draw a perpendicular to the interface at the crossing point and then I mark the angle here, this one as I, and on the sand side I will mark it as R, and then you calculate sin I by sin R, that is equal to 2. Wait, that is just the speed in concrete divided by speed in sand. Now, this is just like a Snell's law. What is the connection here? Oh, the connection is of course the famous Fermat's principle. Now, Fermat's principle for the light says that, this is in geometrical optics, that the light rays would take such a path between 2 points which takes the minimum time, okay, or which takes the shortest amount of time. So, to put it more formally, what I will do is, let us take one say some region. In this region I have these 2 points, okay, and I want to find out which path, if one of the point emits a ray, which path this ray would take to reach point B. The catch is of course that the refractive index here is probably function of the space. It is a inhomogeneous medium. So, in the inhomogeneous medium, and then what happens to the velocity at each point? At each point the velocity of the light would be different and will be given by c by n. Okay. So, what we want to calculate is, first of all, you take any arbitrary path between these 2 points and look at the small length element at some point, and your total time taken for this path is integral from point A to point B of the small line segment divided by the velocity of light at that point. And we can of course readjust this a little and write this as 1 over c integral from A to B n. Of course, remember this is function of the point ds. Okay. And what Fermat's principle says is that of all paths that connect point A and point B, so there could be infinitely many paths which would connect A and B, only that path will be taken by the light for which the time taken is minimum. Okay. So, this is what the Fermat's principle says. And this of course can be used to explain variety of phenomena there, and one of the most common phenomenon that people usually show is that of a mirage. What happens in mirage is that near the ground the air is warm, so the refractive index is higher, and hence the speed of the light is faster near the ground than above the air. So, what would happen is that the ray, while it passes from the source to the observer, it actually goes through a slump like this, because it tries to travel more and more distance near the ground rather than, and then of course, the observer would interpret as if the light rays are coming from the ground, and he sees the reflection of the object even though there is no water or there is no reflecting surface. Okay. The question that we want to ask is this. Now, if there is a Fermat's principle for light, and remember the light is in principle not covered under the classical mechanics. If there is a Fermat's principle for light, why can't I have such a principle, or what is that principle which will apply to the classical systems or classical mechanics? And for that I will take one more example. Now, look at this example of a projectile motion. Now, in this projectile motion, a particle is thrown from point A whose coordinates are 0 0 to the point B here whose coordinates or coordinates of the point B are h 0. Okay. And now I want to pose this problem slightly differently. So, your horizontal range is fixed, you want to throw a projectile from A to B, not just the horizontal range, but the question is to find a path of projectile such that it reaches B in given time, and I will say capital T. Okay. So, we want to find out a path which so normally the problems are posed slightly differently. See, normally you would be given the initial point and the initial velocity, which means the speed and the angle of inclination or angle of projection, and then you are asked to find where it lands and after what time. Here we are posing the problem as a boundary value problem. I have already given you the end points, and I have also said find a path which takes exactly that much amount of time. Now, we of course already know the answer to this. You can immediately put it in. We know the answer is parabolic path and so on, and the answer we already know, and I will call this path as x star t, which is the times t. So, this is and y star t will be equal to half g t times capital T minus t. You can immediately verify that this is the correct equation or correct path for the projectile, and also gives the time dependence. So, at t is equal to 0, the y coordinate will be 0, at t is equal to capital T also y coordinate will be 0, and the at small t equal to 0, x is at 0, and at t is equal to capital T, x star will be equal to h. So, this is the correct path that we know. Okay. Now, what is special about this path is the question we are trying to ask, and that is what is going to be your Hamilton's principle. So, what is special? What I am going to do is, first of all, I will look at few other paths which are nearby. Okay. So, let me define new paths which are x of t, which is equal to h by capital T times t, and y of t, which is half, but instead of g I will put some other number there, a, okay, times t times t minus t. What does this give you? This of course gives you lots and lots of parabolic path. All these paths, remember, start at 0 0, end at point B, which is h comma 0 in time capital T. Okay. But they are different parabolas. So, basically the heights at the midpoint will be different depending on the value of a, and we know only one of those paths is correct path, that is correct path is this when a is equal to g or a by g is equal to 1. Okay, this is the correct path. Now, let me define, since we know the Lagrangian of this system. So, let me write first of all Lagrangian of this system, and the Lagrangian L will be equal to square and minus. So, that would become plus m g times y, sorry, minus m g y. Okay. And I'm of course, we can now apply Lagrange's equations and get that equation, but what I will do is I will define a new quantity called as action. So, definition of action is this. So, for every path from point A to point B, whatever that path may be, we have chosen only a small family of those paths which are only parabolas, but any possible path between A and B which traverses in time capital T, we will assign action A, which of course is function of the path. Okay. So, r of t is nothing but x of t and y of t. We will define this as integral from 0 to capital T L. Remember, L is function of x, y, x dot, y dot and t. Integrate with respect to t. So, what will happen is this integral is of course easy to do. I have already given you x as a function of t, y as a function of t. So, you can calculate x dot, y dot also as functions of t. So, the whole of this can be expressed as a function of t and then you can integrate. Okay. And I will leave that exercise to you people to do. So, after integrating, what we get is action A. And I want to look at this action A for different paths about the actual path that we have found out, which is x star y star. So, if I so these are the various paths that you would get if I change the value of A. For example, the value of A here at the lowest one, here A would be 0 and somewhere in between A is equal to G path is there. That is the correct path. Okay. So, what I want to do is this. For each of these paths, I will plot action, okay, as a function of A by G. You can immediately see what happens here. At A is equal to G or A by G is equal to 1, the action is minimum. See, this is what separates this path from the other paths, and this is in fact the statement of the Hamilton's principle. So, the correct path here is the one for which action is minimum. There you go. Okay. So, I will now pose the statement of the Hamilton's principle. The nature chooses the path of least action, but let us make this more accurate. Okay. So, let us start by defining, consider a system with n particles and n degrees of freedom, and you have looked at all the constraints and everything, and then the system is described by Lagrangian, which is L, okay. And this is of course function of q, q dot and t, and remember each of this q is q1 to qn, because there are n degrees of freedom. Now, let me pose the problem just the way I pose the projectile problem. So, let q1 be a point which is q at t1, and let q2 is another point at t2. So, in the space, okay, I can't draw the configuration space. So, this is a schematic diagram. In this one, I have these 2 points, one point is q1, the other point is q2. The aim is to start from q1 at time t1 and reach q2 at time t2. And then of course, there are infinitely many paths which connect the two, and for each path we assign. So, for each path we assign action which is defined as integral L dt, okay, from T1 to T2. And remember, once I give you path, I give you the time dependence of all the q variables, and from there you can calculate q dot, then the Lagrangian is just merely function of t, you can do this integral. And then the Hamilton's principle says that the actual path of the system is the one for which action as defined there is minimum. Now, this probably is not the most accurate statement. In the following sections, I will refine this definition. It is actually considered as what is called as a stationary point, but this is the Hamilton's principle. And what we are going to do in the remaining sections is this. It is not only this problem. So, Fermat's problem was one, which is some sort of a least time principle. This is a least action principle. Then I can probably think of 2 points in the space, and they ask the question, which is the path which has the shortest distance. So, it is a least distance path problem. So, this is a class of problems which go under the name of variational problems, and the mathematics that underlies all this is called as variational calculus. So, in the next few sections, that is going to be our focus to understand how to solve these problems, variational problems of this kind, and then we will proceed with application to Hamilton's principle. So, in this section, we are going to focus on variational calculus. Now, there are a set of problems which we are interested in, and these problems are called as variational problems. They all fall in this category, okay, which is basically trying to find paths which have something which is minimized. So, in all these problems, there would be some fixed points, and you would be having paths between them. With each path, you assign some quantity called as functional, and then try and find a path for which this functional becomes minimum, or rather extremum. And the history of the variational calculus is also fascinating. You should definitely try and read the way it was developed. So, it begins with Newton, and he was trying to work on a problem where you have a solid surface of revolution, and the surface of revolution, so this particular solid is moving through viscous fluid, and what kind of surface would give you minimal resistance? Something that looks like an aerodynamic problem. You have a vehicle traveling through, or aeroplane traveling through air, and you want to find out what should be the shape of the nose, so that it has a least resistance in the air. The second, after that, about 10 years later, Bernoulli posed his famous brachistochrone problem, and he posed it as an open challenge, and eventually Newton also solved it. This is very interesting reading. And then finally, Lagrange and Euler also worked extensively on this, and Euler is the one who actually coined the name variational calculus. Okay, so let us start by defining the notion of functionals. Okay. So, in the space, I am going to consider only one dimensional case to begin with. So, if you have a space, and I will mark this as a y axis and this as x axis, and you take these 2 points here, and this one is y1 at x1, and this is y2. So, I draw this y2 at x2. Okay. Now, there will be infinitely many paths which join the 2 points x1 y1 to x2 y2, and all these paths basically are continuous or sufficiently smooth functions of x. So, y, the path is represented by a function which is real valued function, it is continuous, it is sufficiently smooth. This we will call it as, so this function is called as is path between y1 and y2. Remember, the x1 x2 is the domain which is fixed and it is given, and what we are going to do is with each path we will assign a quantity called as, so a scalar value j is basically a function from set of all paths between y1 and y2, all paths between y1 and y2 to real numbers. Okay. So, we assign a scalar real number to each possible path. Okay. This is in some sense function of functions. So, the paths themselves are functions and j is basically assigning to each path some scalar value. So, that is why this one has a special name. So, this one is actually called as functional. Okay. And what we are interested in is not any arbitrary functional, but very specific kind of functionals which appear in all the problems that we described earlier or which we will discuss later. Okay, and that is a large class of problems we are interested in. So, I will define this functional which is of very specific kind as a functional which is written as y of x as integral from x1 to x2 of some integrand which I will call it as f, and f is of course function of y dot. Here y dot is derivative of y with respect to x. Commonly we of course write it as y prime, and x dx. So, these are the kind of functionals that we are interested in. Why does it not depend on y double dot? I will leave that question to you to figure that out. Okay. Now, here are some examples. In the first example, think of a plane in which you are given 2 points and we want to find out which path gives the shortest distance between these 2 points. If it is a Euclidean plane, we already know the answer, it is a straight line path between the two. But anyway, we will pose this problem. So, if I take some path between these 2 points, so this is x1 and this is x2. If I take any path, suppose y of x, I immediately can assign the length of the path as, so length of the given path as integral from x1 to x2 and integral over ds. But what is ds? ds is a small element here, and assuming that this is a Euclidean plane, in which case this would become integral from x1 to x2 of dx square plus dy square to the power half, and that I will write as integral from x1 to x2 1 plus y dot square to the power half dx. And now we can immediately identify the integrand. So, your length L is the functional of y, and that is basically integral of the function. So, the integrand function, which is function of y, y dot and x, here is in fact just 1 plus y dot square to the power half. And then the second example is, which we have already seen, which is if we have light traveling from point x1 y1 to x2 y2 in some inhomogeneous field, then we assign with each path for the light rays time of flight between x1 y1 to x2 y2. Again I will write it as t, which is function of the path which is given, as integral, and this is nothing but ds divided by, and from some x1 to x2. Now, this again I will write it as c. So, sorry, I will write this as 1 over c integral from x1 to x2 of, we already know how to write ds, that is nothing but 1 plus y dot square to the power half dx, okay, into n, which is function of x and y. Okay. So, here again we can identify the integrand function. The integrand function, which is function of y, y dot and x, is n, which may depend on x and y, into 1 plus y dot square to the power half. Okay. Now, one more example. This is the famous brachistochrone problem. So, think of a situation where you have the vertical direction and the horizontal direction, and then you have one point here, the other point here, and you have some wire here which connects the 2 points, okay? And then there is a bead. So, what we are going to do is, so there is a gravity pointing downwards. What we are going to do is this: from the upper point you drop the bead with 0 velocity, and it will slide frictionlessly over the wire. The shape of the wire is fixed or is given, and then it would reach the other point here. And question that we want to ask is this: so if this is y1, this one here is y2, this is x1 and this is x2. The question we want to ask is this: what is the shape of the wire which will give me the minimum time of slide? Okay. So, let us pose this. The time taken, so if the shape of the wire is given, then the time taken is equal to, again similar to the previous problem, it is integral from x1 to x2 ds divided by velocity v. But we know velocity v. at each point. So, at each point half mv square must be equal to, so if it has dropped to this point which is y, then clearly this must be equal to mg times y1 minus y, and that immediately gives you velocity v, which is nothing but square root of 2 times g times y1 minus y. Okay. And then I will put it back into this equation. So, this becomes, we already know how to represent ds. So, this is x1 to x2, ds is nothing but 1 plus y dot square to the power half and divided by the velocity now is square root 2g times y1 minus y dx. And in this case the integrand or integrand function is 1 plus y dot square to the power half y1 minus y. And lastly, among the class of these problems, we already have the Hamilton's principle. So, the Hamilton's principle or Hamilton's statement is in fact exactly in the form of a functional. So, here the action in fact is already defined as T1 to T2 of which depends on y dot and t dt. Remember here the role of x will be played by time and y dot here is basically dy by dt, and y of course is posed as function of time t, and this is the path that we are assigning the action to. So, here this is how a functional is assigned to paths, and all these problems what we want to find out is how to extremize, how to minimize the functional, or fondly physicists always say action for every kind of functional. That is the focus of our next section.